This is the problem number 14. In this problem, we need to determine the dimensions of a rectangular building that satisfies certain constraints and minimizes the heat loss. The volume of this building must be exactly 8,000 cubic meters, and we know that the east and west walls lose heat at a rate of 10 units per square meter per day, while the north and south walls lose heat at the rate of 5 units per square meter per day, and the floor loses heat at the rate of 1 unit per square meter per day, the roof at the rate 4 units per square meter per day. The problem is asking to find the dimensions of the building that will minimize the heat loss. Okay, so we know that the building must be a rectangular building. Let's sketch a rectangular building. So this is going to be the base or the floor of the building. That will have a certain height. Okay, and we don't know what the dimensions are. In fact, we're asked to find the dimensions of the building that will minimize the heat loss. So let's use letters X, Y, Z to represent those dimensions. Z will be the height of the building, and then the dimensions of the floor of the building will be X by Y. For concreteness, let's orient our building in some way. So for example, let's assume that the wall that is facing us, that's the south wall. So let's say south is this way. So the opposite wall then of course is the north. And then to the right we have east, and to the left we have west. And now the unknowns, the variables x, y, and z, in this problem are not independent. There is actually a constraint in the problem that these variables have to satisfy. Namely, the volume of the building must be exactly 8,000 cubic meters, and the volume of a rectangular building like this will be simply the product of x, y, and z. And so we have the following condition that the variables x, y, and z must satisfy. X times y times z must equal to 8,000. Next, what we need to express in terms of our variables is the amount of heat that the building will lose each day. So let us denote this amount by H for heat. Now, in principle, it's a function of all three variables, x, y, z, and this is just saying that the amount of heat that the building will lose per day depends on what the dimensions are. But because we said earlier that the variables x, y, z must satisfy this relation, x times y times z equals to 8,000, we can actually solve this for z and express z variable in terms of x and y. Z will be 8,000 divided by x times y. And so if we use that observation and replace z with 8,000 over x times y, in the function h, it will become then a function of only two variables, x and y. Now let's determine the exact algebraic expression that describes calculates the amount of heat lost by this building each day based on these dimensions. So we know we're told in the problem that east and west facing walls are losing heat at the rate of 10 units per square meter per day. And so if we want to calculate the amount of heat lost per day by the east, the amount of heat that exits the building through east and west walls, we need to calculate the area of those walls and then multiply that area by 10 units per square meter. Okay, so we'll have 10 times y times z. Now y times z is the area of the west facing wall. Likewise, we'll have plus 10, again, y times z. The dimensions of east facing wall are exactly the same. It has exact same area, so again, plus 10 times yz. And then for north and south walls, they lose heat at the rate of 5 units per square meter, and since the area of the south and north facing walls is x times z, we get plus 5xz plus 5xz, the amount of heat lost by each by the south facing wall and by the north facing wall. Now finally we need to add to this sum the amount of heat lost through the ceiling and through the roof and through the floor. For the floor, the rate is 1 unit of heat per square meter. The area of the floor is x times y, so we get plus 1 times x times y. This is the heat lost through the floor. And the roof loses heat at the rate of 4 units per square meter per day. So the amount of heat lost through the roof will be 4 times x times y. Let's collect similar terms here. So we get 20 yz plus 10xz, and then plus 5xy. This is h, the heat lost per day, expressed as a function of all three variables, x, y, z. But now let's substitute, instead of z, 800 divided by x over y. Then we will express the amount of heat lost per day by this building only in terms of x and y. So 20y times 8,000 divided by x times y plus 10x multiplied by 8,000 divided by x and y, and then finally plus 5xy. And let's make simplifications. The factor y here and the factor y in the denominator cancel out. Likewise, the factor of x and the factor of x in the denominator cancel out. So we get 5xy plus 20 times 8,000. That's going to be 160,000 divided by x. And then we have plus 80,000 divided by y. And this function calculates the amount of heat lost by our building if the dimensions are x by y by z. Okay, now we want to minimize the amount of heat lost. So therefore, we want to find the minimum value of this function. Okay, so since we're looking for the minimum value of this function, we will begin by finding critical points of this function. Let's calculate the partial derivatives, dh dx and dh dy, and set them both equal to 0. Partial derivative with respect to x will be 5y minus 160,000 divided by x squared, and we set this equal to 0. We can actually solve this equation for y to obtain that y equals 160,000 divided by 5 and by x squared. 160,000 divided by 5, that will be 32,000 divided by x squared. Likewise, let's differentiate with respect to y and set the partial derivative equal to 0. dh dy equals 5x minus 80,000 divided by y squared. We want this partial derivative equal to 0 as well. And we can here solve this equation for x, for example, to get that x equals 16,000 divided by y squared. Okay, now let me summarize these results. We now have the system of the following equations. Y equals 32,000 divided by x squared. And the second equation is that x equals 16,000 divided by y squared. Okay, now let's remind ourselves what the question is asking. So of course we can go ahead and solve this system for x and y. So one way to do that would be to take from the first equation the expression of y in terms of x, 32,000 over x squared, and we can plug that into the second equation instead of y. And that would give us the equation for x, which we can solve. Once we have the value of x, we can plug it into the first equation and solve for y. Now, looking at the question that the problem is asking, it's asking for the height of the building, which is the value of z. Now, in order to find the value of z, we just need to know what x times y is. And so here we can actually save ourselves a little bit of work if we try to solve for x times y without solving for x and y. If you multiply these two equations, x times y equals 32,000 times 16,000 divided by x squared and y squared. Then we can clear denominators by multiplying both sides by x squared and by y squared, and what we're going to get is x times y equal to the third power, xy cubed, equals, on the right hand side, 32 is 2 to the 5th, 16 is 2 to the 4th, and so we get 2 to the power 9 times 1000 squared. And now we can take the cube root of both sides to solve for x times y. X times y will equal to cube root of 2 to the 9th is 2 to the 3rd. Cube root of 1000 is 10, and so the cube root of 1000 squared is going to be 10 squared. And so x times y is 800 at that critical point. Now if we plug that into the equation for z, well, we'll find that z equals 8000 divided by 800, and that is equal to 10. I want to emphasize that this is a shortcut. You don't have to do it this way. You could simply solve for x, solve for y, then you have x and y values, you plug them into the equation for z, and that's going to give you the z value. Okay, now there's one thing that I want to take a look a little bit in more detail. How can we be sure that the critical point that we found this way is a minimum value of this function? This follows from the fact that if you're solving for x and y from the equations that we get from by setting the two partial derivatives to equal to 0, we will find one solution. So this function has only one critical point, and I'm thinking whether it will have one critical point, or yeah, we will have just one critical point. And on the other hand, the function, if x or y or both are close to 0, then it's clear that the values of this function are going to be very large, right? Because the terms such as 160,000 divided by x, if x is very small, then the value of this ratio is going to be very large. Likewise, if y is very small, the value here is going to be very large. Now, if both x and y are very large, then the first term is going to be very large. And so we see that the function takes arbitrarily large values. Therefore, it does not really have an absolute maximum, but it will have a minimum value because taking very large values for x and y is going to give us very large value for the function. Taking very small values for x and y is going to give us a very large value of the function. And so we have to be really looking for the when we're looking for the smallest possible value, we just need to look in some bounded rectangle in the xy plane. And there is a general principle in calculus that we haven't really gone over, which says that on a bounded domain, a function like this will have to have a minimum value. Now, so what this shows is that our function does have an overall absolute minimum value, and therefore it has to be at the critical point. And considering that there is only one critical point here, that is the point that has to be the minimum point. The overall answer for our problem, which was asking what is the height of the optimal building, the correct answer is 10 meters.